Good evening, children. Am I audible? Good evening, children.
Evening, ma'am.
Good evening. Good evening, children. Good evening. Let's recall the theorems which we have understood in the last class. Only 2 students have submitted the assignment. Sangamitra and Pratiksha. Others, please complete the task assigned and submit your classwork soon. Okay, so equal chords of a circle subtend equal angles at the center. Equal chords of a circle. Two equal chords of a circle. If the 2 chords are equal in length, then the angle they make at the center are also equal. So this is the center of the circle. Angle made by this chord at the center. Angle made by this chord at the center. If the 2 chords are equal in length, then the angle they subtend at the center are also equal. Equal chords subtend equal angles at the center. If the angles subtended by 2 chords, the chords are not equal here. If the angles subtended by 2 chords at the center of a circle are equal, if the angles are equal, then the chords are equal. Two chords, we don't know if they're equal in length, but it's known that the angle they subtend at the center are equal. Okay, so this is 50 degrees, this also 50 degrees. This angle is subtended by this chord. This angle is subtended by this chord. The angles subtended by 2 chords. The angles subtended by the 2 chords at the center are equal. Then the chords are equal. Then the chords are equal in length. If the angles subtended by 2 chords at the center of a circle are equal, if the angles are equal, then it means that the chords are also equal in length. The perpendicular from the center of a circle to a chord bisects the chord. Circle, chord, center, perpendicular. Drop a perpendicular from the center to the chord. If you drop a perpendicular from the center to the chord is bisected. Circle, chord, center of the circle, perpendicular. So if you call this chord AB and this one is OM, it's given that OM is perpendicular to AB. OM is a line from the center to the chord and is perpendicular to the chord. OM is a line from the center of the circle to the chord and it's perpendicular to the chord. OM is perpendicular to AB. If OM is perpendicular to AB, that means M is the midpoint of AB. That is, the chord is bisected at M. The perpendicular from the center to the chord. OM is the perpendicular from the center to the chord. The perpendicular bisects the chord. Where does the perpendicular meet the chord at M? So M is the midpoint of AB. Where does the perpendicular meet the chord? It meets the chord at M. The perpendicular meets the chord at M. So M is the midpoint of AB. The perpendicular from the center to the chord bisects the chord. If OM is perpendicular to AB, then M is the midpoint of AB. Conversely, if M is the midpoint of AB, then OM should be perpendicular to AB. If the chord is bisected, if a line from the center to the chord bisects the chord, then the line should be perpendicular to the chord. That's the converse of the theorem. The theorem is, if OM is perpendicular to AB, the perpendicular from the center to the chord bisects the chord. M is the midpoint. M is the midpoint of AB. M is the midpoint of AB. If OM is perpendicular to AB, then M is the midpoint of AB. If it's given that M is the midpoint of AB, if it is given that M is the midpoint of AB, then OM should be perpendicular to AB. If M is the midpoint of AB, if M is the midpoint of AB, then OM should be perpendicular to AB. If a line is drawn from the center of the circle to bisect the chord, then the line should be perpendicular to the chord. If you draw a line from the center of the circle to bisect the chord, then that line is perpendicular to the chord. If M is the midpoint of AB, then OM, because OM is the line from the center, O is the center of the circle, then OM should be perpendicular to AB. Equal chords of a circle are equidistant from the center. If two chords are equal in length, then their distances from the center are also equal. Now see here, chord AB. Distance from the center is always the perpendicular distance from the center. O. Distance from the center is always the perpendicular distance from the center. OM. OM is perpendicular to AB. OM is also the perpendicular distance of the chord AB from the center. From the center, there cannot be any other perpendicular to the chord. There is only one perpendicular. From the center O, there is only one line that can be a perpendicular to the chord. From the center O, there can be one and only one line that can be perpendicular to AB. OM is the perpendicular from the center to the chord, and OM is also the perpendicular distance. OM is also the perpendicular distance of the chord AB from the center O. OM is a perpendicular from the center to the chord. So we know by the theorem that M is the midpoint of AB, because OM is perpendicular to AB, M is the midpoint of AB. That's one thing. But this theorem talks about something else. OM is the distance of chord AB from the center. Distance is always perpendicular distance. So it's the same perpendicular, that perpendicular from the center to the chord, that same perpendicular it is. Okay, so OM is the perpendicular distance of AB from the center. ON is the perpendicular distance of the chord CD from the center. Now the theorem is, if AB is equal to CD, then the distance OM is equal to the distance OM. This is the theorem. Equal chords, if the chords are equal chords are equidistant from the center. If the two chords are equal in length, then their distances from the center are also equal. Converse is, chords that are equidistant from the center are equal. Chords chords that are equidistant from the center. Or you can say chords of a circle. Chords of a circle that are equidistant from the center are equal. So the converse is if OM is equal to ON, that is if the distances of the two chords from the center are equal. If OM is equal to ON, then AB is equal to CD. Then AB is equal to CD. This is the converse. If the perpendicular distances of the two chords from the center are equal, then the chords are equal in length. So equal chords are equidistant from the center. Chords equidistant from the center of a circle are equal in length. So like this, we have three theorems and their converses. Recall this, we did this in the last class. Given a single point, given a point P, or we can draw as many circles as we like passing through this point P. Given 2 points P and Q, again, we can draw as many circles as we like passing through these 2 points P and Q. Number of circles that can be drawn passing through 3 given points. 1 point, many circles can be drawn. 2 points, again, many circles can be drawn passing through 2 given points. Now 3 given points. When we have 3 points, we have 2 cases. The 3 points may be collinear. The 3 points may not be collinear. If the 3 points are collinear, if the 3 given points are collinear, you cannot draw one circle passing through all the 3 points. You cannot draw even one circle. That means no circle can be drawn. Because you can draw a circle passing through 2 points at a time. That third point will be either inside or outside the circle. When we have 3 points, and the points are collinear, no circle can be drawn passing through 3 non-collinear points. You can draw a circle passing through any 2 of them. The third point will lie either inside or outside the circle drawn. Now, when the points are not collinear, when the 3 points are not collinear, okay, when the 3 points are not collinear, there is a unique circle. There is one and only one circle, because we know when the 3 points are not collinear, they go to form a triangle. When the 3 points are not collinear, you can form a triangle. When the 3 points are collinear, no triangle is formed. You can connect them by a straight line. When the 3 points are collinear, no circle can be drawn passing through all the 3 points. You can draw a circle, but one of the points will lie either inside or outside the circle. When the 3 points are not collinear, you can join them to form a triangle. When the 3 points are not collinear, you can join them to form a triangle. And you know, in a triangle, you can join the points to form a triangle. And we know what a circumcircle is. A circle that is drawn passing through the 3 vertices of a triangle. A circumcircle is a circle drawn passing through the 3 vertices of a triangle. You cannot draw, if you try to draw another circle passing through these 3 points, it will be the same circle. You cannot draw a different circle passing through these 3 points. So when 3 points are not collinear, there is a unique circle, or there is one and only one circle that can be drawn passing through three non-collinear points. When the 3 points are non-collinear, they are not collinear, there is one and only one circle that can be drawn passing through these three non-collinear points. We know that three non-collinear points can be joined to form a triangle, and the circle drawn is the circumcircle of the triangle. All right. Example 1, NCRT. Given an arc of a circle, complete the circle. Given an arc of the circle, complete the circle. You first have joined the class late. Given an arc of a circle, complete the circle. Okay. So here. Given an arc of a circle, complete the circle. You're given an arc of a circle. Okay, you need to complete the circle. You need to see, given an arc of the circle, meaning you don't know the center of the circle. You're just given an arc of the circle. You need to complete the circle, for which it is important to locate the center of this arc. Only if you know the center can you complete this arc. We are given an arc of a circle, and the question is to complete the arc, that is, get the circle of which this arc is a part. So to complete the circle, we need to identify the center of the circle. Now, how do we identify the center of the circle? Take 3 points on the arc. That is the first step. Take 3 points, any 3 points on the arc. Say we'll call them A, B, and C. Mark off 3 points A, B, and C on the arc. Mark off 3 points A, B, and C on the arc. Join AB, join BC. Join AB, join BC. Mark off 3 points A, B, and C on the arc. Join AB, join BC. Construct the perpendicular bisector of the chord AB. AB is a chord. AB is a chord. BC is also a chord. AB is a line segment. And since it's a part of an arc, you can call it a chord. AB is a chord. BC is a chord. AB and BC are two chords. Construct the perpendicular bisector of the chord AB. That means using your compass, of course fitted with a pencil. Take radius more than half of AB. Put your compass tip here. Put your compass tip here and here. And you know that. Take radius more than half of AB and cut arcs on either sides of AB and join. Sorry. Okay, so with A and B as centers and radius more than half of AB, draw arcs. So you will get 4 arcs. Draw arcs on either sides of AB. And you'll have to draw a line segment passing through, draw a line passing through these 2 points of intersection of the arcs. You know that. Next, construct the perpendicular bisector of the chord BC. That means with B and C as centers and radius more than half of BC. Because if you take radius less than BC, the arcs will not meet. They'll be like this. They'll not meet. If you take a very small radius, the arcs will not meet. You'll draw the arcs, but they'll not meet. So only when you take more than half of BC will the arcs meet. With B and C, compass tip at B and C. With B and C as centers and radius more than half of BC. So it's like this. So you use your compass, put your compass tip here, draw an arc here, draw an arc here. With the same radius, don't change the radius, with the same radius, put the compass tip here, cut the earlier arcs. Cut the earlier arcs. With B as center. With B as center and radius more than half of BC. Draw an arc above BC and below BC. With the same radius, with C as center and the same radius, cut the earlier arcs. Cut the earlier arcs. And join. Okay, join, but I'm just going to draw the line first and then show the arcs. Let the perpendicular bisectors, the perpendicular bisectors will meet. They will meet. The perpendicular bisectors. So let the perpendicular bisectors meet at O. Now with O as center and OA or OB or OC as radius, complete the circle. You will see that OA is equal to OB is equal to OC. We've identified the center of the circle of which the arc is a part. So OA will be equal to OB will be equal to OC. With O as center and OA or OB or OC as radius, complete the circle. So when you do it, so the center of the circle is the point of intersection of the perpendicular bisectors of any 2 non-parallel chords. If when you take 2 parallel chords, you know, supposing you take 2 parallel chords. Now I can't show you here. I'll take a circle. In a circle, supposing you take 2 parallel chords. Okay, let me do this first. In a circle, if you take, supposing you've drawn a circle using a bangle, then also you don't know the center of the circle, right? When you draw a circle using some circular object, not using a compass. So when you draw a circle using some circular object, you do not know the center of the circle. So then if you want to identify the center of the circle, this is the procedure. You have drawn a circle using a circular object. If you draw a circle using a compass, then you know the center of the circle. You also know the radius of the circle. But when you draw a circle using some circular object like a bangle or anything circular, a plate, a round plate, you don't know the center of the circle. You have a circle, but you don't know its center. You also don't know its radius. Only when you know the center can you measure the radius. So now how do we locate? So now you have this a different situation. You have a circle, you don't know its center. Now let's locate the center of the circle. Now for that, if you take 2 parallel chords, supposing you take 2 parallel chords, okay? You take 2 parallel chords. You construct the perpendicular. See, this is what it is. 2 chords, they're perpendicular bisectors, 2 chords. They're perpendicular bisectors. The perpendicular bisectors will meet. They'll intersect. The point of intersection is the center of the circle. That's all. Two chords. Take two chords. Construct the perpendicular bisector of each of the chords. The perpendicular bisectors will meet. They'll intersect. And the point of intersection is the center of the circle. But just in case you take two parallel chords, you didn't know that they are parallel. You just take two chords and they happen to be parallel to each other. Then what will happen is the perpendicular bisector. Now this is the perpendicular bisector of this chord, and this will be the perpendicular bisector of the other chord. Like you draw the four arcs, 1, 2. Like with this and this as centered, you cut these arcs. With this one and this one as centers. And when you join, you will see that the points are collinear. So where is the center now? The perpendicular bisectors will be coincident. The perpendicular bisectors, they'll not meet like this. They'll not intersect. They are coincident. This is the perpendicular bisector of one chord. The same is the perpendicular bisector of the other chord. So the perpendicular bisectors will coincide. They are intersecting at many points. What do we mean by coinciding? They intersect at multiple points, infinitely many points. Then how do you locate the center? So you should not take two parallel chords. If you take two parallel chords, the perpendicular bisectors of two parallel chords are coincident. So it's not possible to locate the center of the circle. So we do the perpendicular bisector of this chord. Now we do the perpendicular bisector for this chord. You will cut the arcs. You will try to join them. So when you extend the lines, you will see that the perpendicular bisectors are coincident. So where's the center? Which is the center? You can't make out. This is center. This is center. This is center. You can't make out because the two lines are coincident. They lie one over the other. So we need to consider two non-parallel chords. So to be safe, if you take a chord like this, take another one like this. Or better still, take chords like this. Take one chord like this, continue with the same thing like this. So you're sure that the chords are not parallel. So 3 points, A, B, and C. Perpendicular bisector, center of the circle. Construct the perpendicular bisector of AB, chord AB. Construct the perpendicular bisector of chord BC. The perpendicular bisectors will intersect, and the point of intersection is the center of the circle. Is it fine, children? Any questions? Was it Kanishka?
No, no doubt.
No, who was that?
Kanishka, miss.
Yeah, very good, Kanishka. Nice to hear your voice after a very long time. Okay, no questions, huh, children?
No, ma'am. No doubt.
All right, children. Please read the steps. All right, children. Please read the steps of construction. Just what we understood. Given an arc of a circle, complete the circle. So let PQ. We first consider only this portion. First, we'll take up only this piece. Let arc PQ be the given arc of a circle. Locate any point R on the arc PQ, because we already marked the, we've already called the arc PQ, right? We've already called the arc PQ. So just take one more point on it, R. Join P to R, Q to R. You can do like this, children, or you can also take points like this. You can take points like this, PQR. PQR like this also. Like this also. You can take. What I've given here is take an arc PQ. So we already have 2 points P and Q. So mark one more point R on PQ. Join P to R. This is one chord. R to Q. This is the other chord. Let arc PQ. Let arc PQ be the given arc of a circle, because given an arc, no, you're given an arc. You're given an arc. So let arc PQ be the given arc of a circle. So it's enough if you take one more point. Locate any point R on the arc PQ. Locate any point R on the arc PQ. Locate it. Join PR, QR. Join PR, QR. So we got 2 chords. We got 2 chords. Construct the perpendicular bisectors of PR and QR. Construct the perpendicular bisectors of PR and QR. Let the perpendicular bisectors meet at O. Let them meet at O. With O as center and OP, OR, OQ as radius, or okay, this is or anything. With O as center and OP or 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 OQ as radius, complete the circle. Complete the circle. This is a finished one. What you see here is a finished one. All right. Please take a screenshot, children. Done, children?
Yes, ma'am.
Yes, ma'am.
All right.
Yes, ma'am.
Draw different pairs of circles. How many points does each pair have in common? What is the maximum number of common points? Draw different pairs of circles. Draw different pairs of circles, meaning 2 circles. Draw different two circles. Draw different pairs of circles. How many points does each pair have in common? So you draw a pair of circles and check how many points they have in common. Draw another pair of circles. Check how many points they have in common. Draw another pair of circles, as many possible, different types. And in this process, so when you repeat this, when you draw many pairs of circles and identify the number of points they have in common, you will be able to conclude the maximum number of common points they can have. Just think about it, children, just a second. Right, children. So first, let's draw pairs of circles which have no point in common. We'll just follow some procedure or some order. We'll not do something randomly like that. so that we understand what we're doing. So we'll first start with drawing pairs of circles which do not have any point in common. There is no point in common. So you shouldn't draw congruent circles, children. You shouldn't draw two congruent circles. Draw different pairs of circles. You should not take congruent circles, meaning you should not draw a circle and draw one over it. Then there are infinitely many points in common. You should draw different circles. If you draw a circle of radius 5 and another circle of radius 5, then they have infinitely many points in common. They have so many points in common. They have so many points in common. No, we are talking about two different circles. Okay, so we are going to draw circles that have no point in common. So maybe like this, one circle like this, and no point in common. See it? Again, we are talking about the points that lie on the circumference of the circle, not the circular region. We're not talking about the circular region. It's not about these points. When we say points, we are talking only about the points that lie on the circumference of the circle. Okay, so we have a circle. So these are the points on the circle. These are the points. These are the points on the circle. We draw another circle. These are the points on this circle. Is there any point common to these two circles? There is no point. There are many points on this circle. Again, there are so many points on this circle, but there is no point common to both the circles. So this pair of circles have no point in common. When you draw a circle like this and another circle like this. So two circles, we have to draw different pairs. Two different pairs of this, another pair. See, this is one pair. This is another pair. This is another pair of circles. Now this circle has so many points on it. So many points on it. And this circle also has so many points on it. Okay, so many points on it. But is there any point which is common to the two circles? No. There is no point common to the two circles. This circle and this circle, they have nothing in common. So this way you can draw pairs of circles that have no point in common, either like this, one inside the other, or completely outside like this. Such pairs of circles have no point in common. Now let's try to draw pairs of circles that have exactly one point in common. Exactly one point in common. They are called touching circles. Touching circles have exactly one point in common. So let's draw touching circles here. Circles can touch internally or externally. These are circles that touch internally. It looked like there are so many points, in common, but actually it is not so. Okay, there'll be only one point. So these are two circles that touch each other internally. These are two circles that touch each other internally. These are two circles that touch each other externally. No big ones also. Two circles that touch each other externally. Touching circles or circles that touch each other have exactly one point in common. Circles that touch each other, pairs of circles that touch each other will have only one point in common. Touching circles can touch each other or one another internally or externally. So like this, you can draw pairs of circles which have only one point, exactly one point in common. Touching circles, they are not intersecting circles, children. These are not intersecting. These are touching circles. These are touching circles. They are not intersecting circles. Now, let's draw pairs of circles that have 2 points. We saw pairs of circles that have no point in common. We saw pairs of circles that have 1 point in common. No point in common is like this. Nothing common, or like this. Nothing common. No point in common. exactly one point in common are touching circles. So one circle and another circle inside it like this, or one circle and another circle outside it like this. Touch. This is the point in common. This is the point in common. Circles that have 2 points in common are intersecting circles. Pair, you don't take 3 circles. We have to draw pairs. Only 2 circles we should draw at a time. So this is a pair of circles that have exactly 2 points in common. And such circles are called intersecting circles. Intersecting circles. Intersecting circles have 2 points in common. Intersecting circles. 2 circles. This is a pair of circles. They are intersecting circles, and you can see that they have 2 points in common. Now you cannot draw a circle. You cannot draw 2 circles that have 3 points in common. You cannot draw. You try to draw. You cannot draw 2 circles that have 3 points in common. We started with 0, then we saw 1, 2. Now we're trying to draw 3, but we cannot draw. You cannot draw 2 circles that have 3 points in common. So the maximum number of common points is 2. The maximum number of common points is 2. What is the maximum number of common points? 2. Intersecting circles. That happens in the case of intersecting circles, which can have 2 points in common, and this is the maximum number of common points. This is the maximum number of common points. Take a screenshot, children. I think you can read through the slide and take a screenshot.
I took screenshot.
Very good. Please read through the slide. All right. It's one. Suppose you're given a circle. Give a construction to find its center. I think we already discussed this. Earlier in example 1, we were given an arc of a circle and we had to find its center and complete the circle. Here you're given a circle. Suppose you're given a circle. Give a construction to find its center. When you're given an arc, you have to find its center and complete this arc. Okay, so we were talking about parallel chords, right? You should not take 2 parallel chords. So children, so here it's like this. You're given a circle. Read what is given. Suppose you are given a circle. Okay, so I'm given a circle. Given a circle. Give a construction to find its center. So how do you start? Take 3 points. See, you're not given it. You're given a circle. So you're given a circle like this. So how do you start? Take 3 points P, R, and Q. Take 3 points P, R, and Q. It can be A, B, C. It's not that you'll have to mark them like this. Anywhere on the circle, you can take 3 points like this. P, Q, R, A, B, C. Join P to R and R to Q. Perpendicular bisector of PR, perpendicular bisector of QR. The perpendicular bisectors meet at O. O is the required center of the circle. You don't have to complete the circle because you already have the circle. You just have to find the center. O is the required center of the circle. You're given a circle, so you have to start with taking 3 points on the circle, P, R, and Q or P, Q, R. Join them. You have 2 chords. When you join the 3 points, you have 2 chords, P, R and R, Q. Perpendicular bisector of PR, perpendicular bisector of RQ. They will intersect. The point of intersection is the center of the circle. So the point of intersection of the perpendicular bisectors of any 2 non-parallel chords of a circle is the center of the circle. How do you locate the center of the circle? The center of the circle is the point of intersection of the perpendicular bisectors. Is the point of intersection of the perpendicular bisectors of any 2 non-parallel chords of the circle. If 2 circles intersect at 2 points, okay, prove that their centers lie on the perpendicular bisector of the common chord. If 2 circles intersect at 2 points, so 2 circles intersect, intersection itself means 2 points, but they've been very clear here. If 2 circles, okay, so 2 circles intersected 2 points, like this, 2 circles intersected 2 points. Prove that their centers lie on the perpendicular bisector of the common chord. This is the common chord. When you join the points of intersection, that will be the common chord. Common chord meaning this is a chord to the first circle as well as the second circle. For the first circle, it's the chord here. For the second circle, it's the chord here. Common chord is the line segment that connects the 2 points of intersection. Circle, intersecting circles, points of intersection. When you join the points of intersection, when you join the points of intersection, that is a common chord. That's the chord common to the 2 circles. But we need to prove that their centers lie on the perpendicular bisector of the common chord. So this is the center of one circle. Meaning we'll have to prove this. O center of the first circle, O dash center of the second circle. We need to prove that O dash is the perpendicular bisector of the common chord. We need to prove that O dash is perpendicular to the common chord. Also, O dash bisects the common chord. Perpendicular bisector. There are 2 things here. One is, okay, let me call this AB. AB. One is see, we have to consider 2 intersecting circles. Okay, that's the first thing. 2 intersecting circles. A and B are the points of intersection. When you join A and B, AB is the common chord to the 2 circles. O is the center of the first circle, O dash is the center of the second circle. We need to get these results. We need to prove these results. O dash is perpendicular to the common chord AB. Also, O dash bisects the common chord AB. We need to prove that O dash is perpendicular to AB. That means this is 90 here, like this. Prove that this is 90. O dash is perpendicular to AB and O dash bisects AB. That is, if we mark this, say like M. AM is equal to MB. The chord is bisected, not O dash. Not O dash. It's not O dash. It's not OM is equal to O dash M. No, no, no. The perpendicular bisector is not bisected. The chord is bisected. Please get the difference. O dash is not bisected. The chord AB is bisected. So we need to prove that O dash is perpendicular to AB. O dash bisects AB, cuts AB into two equal halves. Is the situation clear, children? Why so hesitant to say yes or no? No means no.
Yes, ma'am. Yes, ma'am.
All right. Class, use the emoji. Raise your hand. Vasudevan, Nikita, Sangamitra, Hitesh, Pratiksha, Shreya, Sarar, Nivedita, Kanishka, Ananya. What about Tarun and Shivani? What about Tarun and Shivani? Are you there? Okay. All right, children. So, two circles, intersecting circles, common chord. AB is the common chord. Now, to get this result, children, we normally take constructions, right? We say construction, join this, join that, or we do make use of, we take the help of something to get certain results. So here, AB is a chord, all right? How many AB is a chord and it's a line segment. How many midpoints can a line segment have? How many midpoints can a line segment have? Children, please answer.
One, ma'am.
How many midpoints? Now, supposing AB measures 10 centimeters. Where will the midpoint be located?
5 centimeters.
At 5 centimeters.
5 centimeters.
Yeah, so every line segment has one and only one midpoint. I'm not asking for a line. I'm not asking for a line segment. A line segment has one and only one midpoint. We all know that. You will not ask me how or prove it. We all understand that. A line segment can have only one midpoint. So construction is something like that. Construction is something which is unique, something which all of us will agree. Now, supposing now when I say A and B are the points of intersection and I say join AB, will anyone ask, well, how can you join AB? It's not possible. Nobody has that doubt. You all know it is possible to join AB and get the line segment AB, which is the common chord AB. Construction is something which is unique. Meaning there is no alternative. It's not that why that can something else is also can be true. When I say mark off the midpoint of AB, there is only one midpoint. So that can be a construction. Locating the midpoint of AB is a construction because it's unique. Something which is not unique cannot be taken as a construction. If you have a question like how can you do that or how is it even possible, that cannot be a construction. So construction is something that helps you to get the result. And here the construction is locate the midpoint of AB. Let M be the midpoint of AB. We're just taking help of the midpoint. Nothing else we're doing. See here. We are not saying that something is the perpendicular, a line segment bisects. We are not saying that some line segment bisects AB at M. No, we are just, there is the line segment AB. And we know AB is a line segment, so it has one midpoint, only one midpoint. We're just marking off that midpoint. Let M be the midpoint of AB. Now, this circle has a center, O dash, or some O. This circle has a center, O dash. We've just marked the centers, nothing we've done. Just mark the centers. O and O dash. O and O dash are the centers. Okay. Now, can you join O to M? Join O to M. See, it can also be like this, you know, it can also be like this. There is M here, there is O here, there is O dash here, and meaning it can be a broken line like this also. OM O dash need not be a straight line. That's what we are going to prove now, that it's a straight line. See, okay, let me make it more clear. Like if this is M, maybe this is O and this is O dash. And you know, it's like when you join, it's like something like this. It may be that OM O dash is not a OM O dash is not a straight line. OM and then MO dash. It may be possible that OM O dash is not a straight line. Okay, so what are we doing now? We are just again the construction is join O and M. That's possible. You can join these 2 points. Join O dash M. Yeah, that also is possible. You can join 2 points. That's unique. Now, I am not saying that OM O dash is a straight line. I'm not saying that. We're going to prove that. We are not here. We have not assumed that when you join OM and O dash M, OM O dash is a straight line. That we cannot say, because it can also be something like this. It can also be something like this. That we cannot say. Let me come again. Let M be the midpoint of AB. Circle, we know the centers. We know that O is a center, O dash is a center. Next, join OM. Join O dash M. Now here it looks like it's a straight line because we are going to prove it's a straight line. But we have not assumed so. We have not assumed so. Join OM, join O dash M. OM O dash may be a broken line, but we are going to prove it's a straight line. Okay. So now what have we done? Join OM, join O dash M. Now, OM is a line from the center to the midpoint of the chord. OM is a line from the center to the midpoint of the chord, because let M be the midpoint of AB, we said. OM is a line from the center to the midpoint of the chord, so it should be perpendicular to the chord. The line from the center to bisect a chord is perpendicular to the chord. Similarly, O dash M is a line from the center O dash to the midpoint of the chord AB. It's a line from the center to the midpoint of the chord. That is, it's a line from the center and it bisects the chord. So it should be perpendicular to the chord. So we get angle OMA is equal to 90 degrees. Angle O dash MA is also 90 degrees. OMA is 90, O dash MA is also 90. So that means angle OMA plus angle O dash MA is equal to 90 plus 90, 180. But OMA plus O dash MA is equal to OMA plus O dash MA. If the sum of these two angles is 180, that means OMA plus O dash MA is OMO dash. OMO dash. OMO dash is equal to 180. The measure of this angle is 180. That means OMO dash is a straight line. We've got OMO dash measures 180 degrees. That means OMO dash is a straight line. Now we know that OO dash is perpendicular to AB. And since M is the midpoint, OO dash bisects AB. So OO dash is the perpendicular bisector of AB. So this theorem is when we have two intersecting circles. When we have two intersecting circles, the line segment joining the centers is the perpendicular bisector of the common chord. In two intersecting circles, the line segment, or you can say line, the line joining the centers or the line segment joining the centers, the line or the line segment joining the centers is the perpendicular bisector of the common chord. Is the perpendicular bisector of the common chord. Common chord. The line segment joining the centers, the perpendicular bisector of the common chord. This one is equal to this one. Take a screenshot, children. You will find the same thing here. I'll explain again. Take a screenshot.
It took, ma'am.
Yeah. Okay, so you can see it here that we have to take two circles with centers O and O dash, which intersect at the points A and B, because we are given here. If two circles intersect at 2 points, so we have to take two circles that intersect at 2 points. So two circles with centers O and O dash, which intersect. We are given two circles with centers O and O dash, which intersect at A and B. And then there is some common chord here. So AB is the common chord. AB is the common chord. So circle. AB is the common chord. AB is the common chord. Centers O and O dash. To prove that OO dash is the perpendicular bisector of the common chord AB, we need to prove that OO dash is the perpendicular bisector of the common chord AB. Construction. Let M be the midpoint of AB. Let M be the midpoint of AB. Join OM, join O dash M. Join OM, join O dash M. A line drawn from the center of the circle to bisect the chord is perpendicular to the chord. So this is the theorem which we're going to use to get these results. OM is perpendicular to AB. How do we get this result? By the theorem. OM is perpendicular. OM is perpendicular to AB. How do we get this result? By the theorem. How by the theorem? Because OM is a perpendicular. OM is a line from the center to bisect the chord. So it's perpendicular to the chord. We're using this theorem. What is OM? It's a line from the center which bisects the chord AB. So it should be perpendicular to AB. OM is perpendicular to AB by the theorem. That means if OM is perpendicular to AB, angle OM is 90 degrees. O dash M is perpendicular to AB by the same theorem. You should state the theorem here. See, I've stated the theorem and then I gave the reason by theorem. Because O dash M is a line segment from line or line segment, children, you can use it. interchangeably. O dash M is a line from the center to bisect the chord. It's a line drawn from the center to bisect the chord. So it's perpendicular to the chord. So O dash MA is equal to 90 degrees. So when you add both, you get, when you add both OMA, O dash MA, you get OM, O dash. Because OMA plus O dash MA is equal to OM, O dash. So because this one plus this one is 180, it means that OM, O dash is a straight line. That is, you can just include this. You can include this. OM, O dash is equal to 180. OM, O dash is equal to 180, which means OM, O dash is a straight line. Is a straight line. So now you'll have to mention why it's a perpendicular bisector. So I've mentioned these two again. M is the midpoint of AB by construction and OMA is 90 degrees. M is the midpoint and this is perpendicular 90 degrees. So from 1 and 2, because midpoint and perpendicular, so perpendicular bisector. Midpoint and perpendicular, so perpendicular bisector. See, this is perpendicular and midpoint, so bisector. M is the midpoint of AB by construction. Angle OMA is equal to 90 degrees. So from 1 and 2, OMO dash is the perpendicular bisector of AB. OMO dash is a straight line. It's a straight line. We proved that its measure is 180 degrees. So the line segment joining the centers is the perpendicular bisector of the common chord. So supposing, a figure is given like this to you and supposing this is given to be 8, AM is 8 and BM is 8. AM is 8 and BM is 8. What's the measure of angle? OMA. OMA is equal to 90 degrees. This is the common chord. This is the common chord. It's bisected, so it has to be perpendicular. OMA is equal to 90 degrees. Take a screenshot, children. Already taken, is it?
Yes, ma'am.
Yeah.
Yes,
I said
ma'am.
you can already. 1 second. I said you can also include this angle OMO dash is equal to 180. Yes, Shreyas.
Ma'am, I can't understand this question. Ma'am.
Yeah, read the question. Read the statement.
Ma'am, question or the given statement, ma'am?
Yeah, now you can see that the centers lie on the perpendicular bisector of the common chord. The centers lie on the perpendicular bisector, meaning the line segment joining the centers is the perpendicular bisector of the common chord. Yes, Shreyas, you can go on. Read what you don't understand, I'll tell you.
Ma'am, no, ma'am, I can't understand that whole proof itself, ma'am. How that OMA we are concluding as 90 degrees.
Okay, can I suggest one thing, if you don't mind, because sometimes overdoing something, I don't think it will really get into someone's head. It will just go above it. I'll share the recording by 9 today. Why don't you just watch the last, I think now the time is 7:05 or 7. If you watch the last 15 to 20 minutes of the recording, you will find this explanation. Why don't you just watch it and get back tomorrow?
Okay.
Yeah. It's not about explaining again. Numericals is a different story. The proof I have to repeat again, which might not be clear because it's kind of stuffing the same thing into your ears. Let me just give you some time. You watch the recording and get back to me. Don't forget. Yeah. Example 2. If two intersecting chords of a circle make equal angles with the diameter passing through their point of intersection, prove that the chords are equal. If two intersecting chords of a circle, so here we assume that the chords intersect inside the circle, okay? It's not outside the circle. What I mean to say is, when you have two chords like this, these two chords, they don't meet inside the circle, but they'll meet when you produce, they'll meet outside the circle. We are not talking about this case. When you consider two chords, two intersecting chords, now these are two chords. These are two chords of a circle which don't meet inside the circle. When you produce them, they meet here. Not this case. We are talking about two chords that intersect inside the circle itself. We are talking about two chords that intersect inside the circle itself. Circle, chord. We need to prove that the chords are equal, children. The chords are equal in length. So somewhat equal, I should make them look like. So these are two chords of a circle, and these are two intersecting chords of a circle. Now we need to take the diameter that passes through their point of intersection. We know that the diameter passes through the center. So let's mark the center. We know that the diameter of a circle passes through the center. Now we need to take the line, which is a diameter. We need to take up the diameter. Diameter means it passes through the center. So we need to take the diameter that passes through the point, that passes through their point of intersection. So this is the diameter passing through their point of intersection. Because diameter means it should pass through the center. It should also pass through their point of intersection. So this is the diameter. You can draw many diameters in the circle, but you should draw that diameter which passes through their point of intersection. It's given that the two chords make equal angles with this diameter. That is, this is the diameter, this is the diameter, this is the diameter. This is the chord. This is one of the chords. This is one of the chords. This is the diameter. One of the chords is the diameter, this angle. This is the angle between the diameter and one chord. This is the other chord. This is the other chord. This is the diameter. This is the angle between the diameter and the other chord. If these two angles are equal, if angle 1 is equal to angle 2, you must prove that the chords are equal in length. You must prove that AB is equal to CD. Chord diameter angle. Chord diameter angle. This angle. This is the diameter. One chord, the other chord. This is one chord. This is the diameter. This is the diameter. This is one chord. This is one chord. This is the diameter. This is the angle between the chord and the diameter. This is the other chord. This is the diameter. This is the angle between the other chord and the diameter. If these two angles are equal, if angle 1 is equal to angle 2, then prove that AB is equal to CD. If two intersecting chords of a circle make equal angles, they make equal angles. With whom? With the diameter. But there are so many diameters. With the diameter passing through their point of intersection. With the diameter passing through their point of intersection. So it's now clear which diameter it is. Because equal angles with the diameter means which diameter? So that diameter which passes through the point of intersection. Their intersection. Okay, I hope the diagram is clear. The diagram is mostly given. Just in case it's not given, you should know how to make it. So, circle, one chord, another chord, point of intersection, center of the circle, diameter that passes through their point of intersection, chord, diameter, angle 1. Chord, diameter, angle 2. If angle 1 is equal to angle 2, prove that AB is equal to CD. Prove that AB is equal to CD. Now, when we work with circles, the default construction is dropping perpendiculars from the center to the chords. Because it's unique. It's unique. Whenever we work with circles, this particular chapter, default construction is drawing the perpendiculars from the center to the respective chords. So, center, perpendicular. This is one chord. AB is one chord. Draw OM perpendicular to AB. Construction. Draw ON perpendicular to CD. Construction. That's a default construction. Draw OM perpendicular to AB. Draw ON perpendicular to CD. Now we have two triangles. Let's mark this point also. Let's call it P. Now we have two triangles OMP, ONP. We have two triangles OMP, ONP. You can show that these two triangles are congruent to each other. You know that very well. You know that very well. You know how to prove that the. Okay, one of you tell me, how do we show that triangle OMP is congruent to triangle ONP? Yes, class. Why no response, children? You're not happy with me. You're not happy with the chapter. What is that which is, not allowing you to share your thoughts? Huh? You must also understand the plight of the teacher. There is somebody talking from the other end. And occasionally when questions are shooted, you still don't want to answer.
Miss.
Yes, children. Yes, who's that? Kanishka. Go on, Kanishka.
Ma'am, angle 1 is equal to angle 2.
Very good. Angle 1 is equal to angle 2 given. Next, Kanishka.
Then 90 degree, ma'am, angle M and N.
Correct. Angle OMP is equal to angle O.
NP, ma'am.
NP. Angle OMP of the of one triangle is equal to angle ONP of the other triangle, 90 degrees. Construction. Very good. Then.
And then OP is equal to OP, ma'am. They are common.
Very good. Oh, thank you, Kanishka. So OP is equal to OP, common side. So what's the congruence rule?
AAS, ma'am.
AAS rule. AAS rule, the two triangles are congruent. So see now, children. Okay, Kanishka, now we'll have to prove that the chords are equal. When are the chords equal, Kanishka? When they are equidistant from the center, right?
Yes, ma'am.
Okay, see, if you want to prove that the chords are equal, you don't have to directly prove that they are equal. Even if you prove that they are equidistant from the center, then also they are equal. Either you have two options. Either you can directly say AB is equal to CD, but that's not possible because AB and CD are not, sides of the two triangles which we have taken up. The two triangles are so little. AB and CD are not parts of the two triangles. So you cannot directly say CP, CTC, AB is equal to CD. But that's the result you need to prove. So what is the other way? Prove that the distances from the center are equal. Which line segment represents the distance of AB from the center, Kanishka? Which is the line segment that represents the distance of AB from the center?
AB, ma'am.
AB.
OP, ma'am.
No, darling, not OP. Class. Which line segment represents the distance
Sorry,
of AB?
OM, ma'am.
OM is the perpendicular distance of AB from the center. And what is the distance of CD from the center?
ON, ma'am.
OM is the distance of
AB, ma'am.
Yeah, OM is the perpendicular distance of AB from the center. ON is the perpendicular distance of CD from the center. We want to prove that AB is equal to CD, but CP-CTC we can't get this. But CP-CTC we can get this. OM is equal to ON. Can we get that through CP-CTC?
Yes, ma'am.
Yeah, OM is equal to ON. Now you will think it's out of way. Why should we prove that OM is equal to ON? Because we are not getting AB is equal to CD. That's what we have to prove. AB is equal to CD. That we are not getting. So what's the other way of proving AB is equal to CD? Their distance from the center. Their distance. AB's distance from the center is OM. CD's distance from the center is ON. So can we get OM is equal to ON? Yes, very much we can. OM is equal to ON CP-CTC. So now we'll have to state the theorem. Chords that are equidistant from the center. Chords of a circle that are equidistant from the center are equal. And here OM is equal to ON. That means the distances are equal. Therefore, AB is equal to CD. Therefore, AB is equal to CD. Take a screenshot, children.
I took mine.
Yeah. I have not marked angle 1 and 2 here, children.
1 second.
Yeah.
Completed.
Yeah. This is angle 1, children. This is angle 1, this is angle 2. Take a screenshot with the numbers 1 and 2.
Yes, ma'am. Took ma'am.
Yes,
ma'am. Took ma'am.
So same thing, what we discussed. Chords meet at E with angle 1 is equal to angle 2. We understood why, because they make equal angles with the diameter passing through their point of intersection. Angle 1 is equal to angle 2. To prove that AB is equal to CD, construction is drawing the perpendiculars from the center to the chord. Then show that the triangles are congruent. CP-CTC, LO is equal to MO. That means AB is equal to CD. Chords equidistant from the center are equal. All right, children. So that's it for today's session. Thank you so much, children.
Thank you,
Thank you, ma'am.
Thank you, children. Thank you.
Thank you.
Thank you, ma'am.
Ma'am, we want to write and send it now, ma'am.
Yeah, children, please complete your work
Okay, ma'am.
by tomorrow's class. Yes.